Ever wonder how your phone recognizes your face, or how AI translates languages in real time? It all starts with a mind-bending mathematical concept called the Universal Approximation Theorem. Let's unravel why this theorem is foundational to neural networks, and how a groundbreaking technique called PLN is redefining what these networks can achieve. Imagine teaching a neural network to draw a curve. The Universal Approximation Theorem states, if you give it enough neurons, it can mimic any curve, whether it's a straight line, a wiggly sine wave, or something entirely novel. Think of it like a kid with Lego bricks. The more pieces you have, the more complex the structure you can build. But here's the catch. Traditional proofs of this theorem focus on linear layers and basic activation functions like ReLU or sigmoid. They ignore something critical in modern AI, normalization layers. Normalization layers, like batch normalization or layer normalization, are the unsung heroes of deep learning. They stabilize training by adjusting inputs to a consistent scale, preventing values from exploding or vanishing. But do they just make training easier, or do they enhance the network's ability to model complex functions? This is where parallel layer normalization, PLN, comes in. Developed by researchers at Beihang University, PLN isn't just another normalization trick, it's a paradigm shift. Think of it as a supercharged activation function that also normalizes data. Here's the key innovation. It groups neurons into smaller clusters and normalizes them in parallel. This isn't about speed alone, it's about giving the network a more powerful tool to approximate functions. The research shows that an infinitely wide PLN network can approximate any function, just like traditional networks. But here's the twist, it achieves this with fewer neurons. For example, modeling a smooth function like a gentle hill might require half the neurons of a standard network. It's like building the same Lego structure with half the blocks, smarter, not harder. Why does this matter? Neural networks are the engines of AI, and efficiency is everything. By combining activation and normalization into one step, PLN simplifies designs and boosts performance. The team tested it on real-world models like CNNs and transformers, and PLN didn't just match traditional methods. In some cases, it outperformed them. This isn't just theory. It's why your smart speaker understands your voice, why doctors use AI to spot tumors, and why chess bots can beat grandmasters. The math proves neural networks aren't guessing. They're systematically learning the rules of complexity. It's like giving a robot a paintbrush and letting it recreate Van Gogh, but with numbers. So what's the takeaway? The Universal Approximation Theorem still holds, but PLN shows modern techniques can make neural networks even more powerful. It's a reminder that AI isn't just about brute force. It's about smart, efficient innovation. Thanks for watching. If you want to dive deeper into how AI learns, hit subscribe. And drop a comment below. What's one thing you'd love to see AI master next? Until next time, keep exploring.